Learning objectives. In this chapter, the user would learn the following in detail. The multicast backbone, M-bone, link state multicast, distance vector multicast, reverse path broadcast, reverse path multicast RPM, protocol independent multicast PIM, multi-protocol label switching MPLS, destination-based forwarding, explicit routing, virtual private networks VPNs, and tunnels. Distance vector multicast. Distance vector multicast routing protocol DVM-RP. The distance vector multicast routing protocol DVM-RP is a distance vector routing protocol designed to support the forwarding of multicast datagrams through an internetwork. DVM-RP constructs source-rooted multicast delivery trees using variants of the reverse path broadcasting RPB algorithm. Some version of DVM-RP is currently deployed in the majority of the M-bone routers. The original specification was derived from the Routing Information Protocol (RIP) and employed the truncated reverse path broadcasting TRPB algorithm. The major difference between RIP and DVM-RP is that RIP is concerned with calculating the next hop to destination, while DVM-RP is concerned with computing the previous hop back to a source. Physical and tunnel interfaces. The ports of a DVM-RP router may be either a physical interface to a directly attached subnetwork or a tunnel interface to another multicast island. All interfaces are configured with a metric that specifies the cost for the given port and a TTL threshold that limits the scope of a multicast transmission. In addition, each tunnel interface must be explicitly configured with two additional parameters: the IP address of the local router's interface and the IP address of the remote router's interface. A multicast router will only forward a multicast datagram across an interface if the TTL field in the IP header is greater than the TTL threshold assigned to the interface. Below table lists the conventional TTL values that are used to restrict the scope of an IP multicast. Basic operation. DVM-RP implements the reverse path multicasting RPM algorithm. According to RPM, the first datagram for any source group pair is forwarded across the entire internetwork, provided that the packet's TTL and router interface thresholds permit. The initial datagram is delivered to all leaf routers, which transmit prune messages back towards the source if there are no group members on their directly attached leaf subnetworks. The prune messages result in the removal of branches from the tree that do not lead to group members, thus creating a source-specific shortest path tree with all leaves having group members. After a period of time, the pruned branches grow back and the next datagram for the source group pair is forwarded across the entire internetwork, resulting in a new set of prune messages. DVM-RP implements a mechanism to quickly graft back a previously pruned branch of a group's delivery tree. If a router that previously sent a prune message for a source group pair discovers new group members on a leaf network, it sends a graft message to the group's previous hop router. When an upstream router receives a graft message, it cancels out the previously received prune message. Graft messages can cascade back toward the source, allowing previously pruned branches to be restored as part of the multicast delivery tree. DVM-RP router functions. When there is more than one DVM-RP router on a subnetwork, the dominant router is responsible for the periodic transmission of IGMP host membership query messages. Upon initialization, a DVM-RP router considers itself to be the dominant router for the subnetwork until it receives a host membership query message from a neighbor router with a lower IP address. In order to avoid duplicate multicast datagrams, when there is more than one DVM-RP router on a subnetwork, one router is elected the dominant router for the particular source subnetwork. In below figure, DVM-RP dominant router, router C is downstream and may potentially receive datagrams from the source subnetwork from router A or router B. If router A's metric to the source subnetwork is less than the router B's metric, router A is dominant to router B for this source. This means that router A forwards traffic from the source subnetwork and router B discards traffic from the source subnetwork. However, if router A's metric is equal to router B's metric, the router with the lowest IP address on its downstream interface child link becomes the dominant router. DVM-RP routing table. Since the DVM-RP was developed to route multicast and not unicast traffic, a router may be required to run multiple routing processes, one for the delivery of unicast traffic and another for the delivery of multicast traffic. The DVM-RP process periodically exchanges routing table update messages with the multicast capable neighbors. These updates are independent of those generated by any interior gateway protocol that provides support for unicast routing. DVM-RP relies on the receipt of Poisson reverse updates for leaf router detection. This technique requires that a downstream neighbor advertise infinity for a source subnetwork to the previous hop router on its shortest path back to that source subnetwork. If an upstream router does not receive a Poisson reverse update for the source subnetwork on a downstream interface, the upstream router assumes that the downstream subnetwork is a leaf and removes the downstream port from its list of forwarding ports. Unlike the typical table created by a unicast routing protocol such as RIP, the DVM-RP routing table contains source subnets and from gateways instead of destinations and next hop gateways. The routing table represents the shortest path source routed spanning tree to every participating subnetwork in the internetwork, the reverse path broadcasting RPB tree. The DVM-RP routing table does not consider group membership or received prune messages. Link state multicast, link state OSPF. Link state routing is the second major class of intra-domain routing protocol. Each node is assumed to be capable of finding out the state of the link to its neighbors up or down and the cost of each link. The basic idea behind link state protocols is very simple. Every node knows how to reach its directly connected neighbors, and if we make sure that the totality of this knowledge is disseminated to every node, then every node will have enough knowledge of the network to build a complete map of the network. This is sufficient condition for finding the shortest path to any point in the network. Thus, link state routing protocols rely on two mechanisms: reliable dissemination of link state information and the calculation of routes from the sum of all accumulated link state knowledge. The difference between the distance vector and link state algorithms can be summarized as follows. In distance vector, each node talks only to its directly connected neighbors, but it tells them everything it has learned. In link state, each node talks to all other nodes, but it tells them only what it knows for sure. Reliable flooding. Reliable flooding is the process of making sure that all the nodes participating in the routing protocol gets a copy of the link state information from all the other nodes. As the term flooding suggests, the basic idea for a node to send its link state information out on all of its directly connected links, with each node that receives this information forwarding it out on all of its links. This process continues until the information has reached all the nodes in the network. Each node creates an update packet, also called a link state packet (LSP), that contains the following information: the ID of the node that created the LSP, the list of directly connected neighbors of that node with the cost of the link to each one, a sequence number, a time to live for this packet. The first two items are needed to enable route calculations. The last two are used to make the process of flooding the packet to all nodes reliable. Reliability includes making sure that you have the most recent copy of the information, since there may be multiple contradictory LSPs from one node traversed in the network. As in RIP, each node generates LSPs under two circumstances: expiry of a periodic timer, or a change in topology can cause a node to generate a new LSP. One of the important design goals of a link state protocol's flooding mechanism is that the newest information must be flooded to all nodes as quickly as possible, while old information must be removed from the network and not allowed to circulate. In addition, it is clearly desirable to minimize the total amount of routing traffic that is sent around the network. After all, this is just overhead from the perspective of those who actually use the network for their applications. One easy way to reduce overhead is to avoid generating LSPs unless absolutely necessary. This can be done by using very long timers, often on the order of hours, for the periodic generation of LSPs. To make sure the old information is replaced by newer information, LSPs carry sequence numbers. Each time a node generates a new LSP, it increments the sequence number by 1. LSPs also carry a time to live. This is used to ensure that old link state information is eventually removed from the network. A node always decrements the TTL of a newly received LSP before flooding it to its neighbors. It also ages the LSP while it is stored in the node. When the TTL reaches 0, the node refloods the LSP with a TTL of 0, which is interpreted by all the nodes in the network as a signal to delete that LSP. Flooding of link state packets. A. LSP arrives at node X. B. X floods LSP to A and C. C. A and C flood LSP to B, but not X. D. Flooding is complete. Route calculation. Once a given node has a copy of the LSP from every other node, it is able to compute a complete map for the topology of the network, and from this map it is able to decide the best route to each destination. A well-known algorithm from graph theory, Dijkstra's shortest path algorithm, is used to calculate routes from this information. The Dijkstra's shortest path algorithm is defined as follows. N denotes the set of nodes in the graph. I of I, j denotes the non-negative cost weight associated with the edge between nodes I, j set of all n, I of I comma j is equal to infinity if no edge connects I and j. S set of all n denotes this node, that is, the node executing the algorithm to find the shortest path to all the other nodes in n. M denotes the set of nodes incorporated so far by the algorithm. C of n denotes the cost of the path from S to each node n. The algorithm works as follows. Initialize the confirmed list with an entry for myself. This entry has a cost of 0. For the node just added to the confirmed list in the previous step, call it node next, select its LSP. For each neighbor of next, calculate the cost to each this neighbor has the sum of the cost for myself to next and from next to neighbor. If neighbor is currently not on either the confirmed or the tentative list, then add neighbor cost next hop to the tentative list, where next hop is the direction I go to reach next. If neighbor is currently on the tentative list and the cost is less than the currently listed cost for neighbor, then replace the current entry with neighbor cost next hop, where next hop is the direction I go to reach next. If the tentative list is empty, stop. Otherwise, pick the entry from the tentative list with the lowest cost, move to it the confirmed list, and return to step 2. Link state routing, an example network. Open Shortest Path First Protocol OSPF. One of the most widely used link state routing protocols is OSPF. The first word open refers to the fact that it is an open, non-proprietary standard created under the auspices of the IETF. The SPF part comes from an alternative name for link state routing. OSPF adds quite a number of features to the basic link state algorithm described above, including the following: authentication of routing messages, additional hierarchy, load balancing. Authentication of routing messages. It is all too common for some misconfigured host to decide that it can reach every host in the universe at a cost of 0. When the host advertises this fact, every router in the surrounding neighborhood updates its forwarding tables to point to that host, and said host receives a vast amount of data that, in reality, it has no idea what to do with. It typically drops it all, bringing the network to a halt. Such disasters can be averted in many cases by requiring routing updates to be authenticated. Early versions of OSPF used a simple 8-byte password for authentication. This is not a strong enough form of authentication to prevent dedicated malicious users, but it alleviates many problems caused by misconfiguration. Additional hierarchy. Hierarchy is one of the fundamental tools used to make systems more scalable. OSPF introduces another layer of hierarchy into routing by allowing a domain to be partitioned into areas. This means that a router within a domain does not necessarily need to know how to reach every network within that domain. It may be able to get by knowing only how to get to the right area. Thus, there is a reduction in the amount of information that must be transmitted to and stored in each node. Load balancing. OSPF allows multiple routes to the same place to be assigned the same cost and will cause traffic to be distributed evenly over those routes. The version field is currently set to 2. The type field may take the values 1 through 5. The source adder identifies the sender of the message. The area ID is a 32-bit identifier of the area in which the node is located. The authentication type is 0 if no authentication is used. Otherwise, it may be 1, implying a simple password is used, or 2, which indicates that a cryptographic authentication checksum is used. The authentication field carries the password or cryptographic checksum. OSPF link state advertisement. Packet format for a type 1 link state advertisement. Type 1 LSAs advertise the cost of links between routers. Type 2 LSAs are used to advertise networks to which the advertising router is connected, while other types are used to support additional hierarchy. The LS age is the equivalent of a time to live, except that it counts up and the LSA expires when the age reaches a defined maximum value. The type field tells us that this is a type 1 LSA. In a type 1 LSA, the link state ID and the advertising router field are identical. Each carries a 32-bit identifier for the router that created this LSA. While a number of assignment strategies may be used to assign this ID, it is essential that it be unique in the routing domain and that a given router consistently uses the same router ID. One way to pick a router ID that meets these requirements would be to pick the lowest IP address among all the IP addresses assigned to that router. The LS sequence number is used to detect old or duplicate LSAs. The LS checksum is used to verify that data has not been corrupted. It covers all fields in the packet except LS age, so that it is not necessary to recompute a checksum every time LS age is incremented. Length is the length in bytes of the complete LSA. Each link in the LSA is represented by a linked ID, some link data, and a metric. The first two of these fields identify the link. A common way to do this would be to use the router ID of the router at the far end of the link as the link ID, and then use the link data to disambiguate among multiple parallel links if necessary. The metric is, of course, the cost of the link. The type tells us something about the link, for example, if it is a point-to-point link. The TOS information is presented to allow OSPF to choose different routers for IP packets based on the value in their TOS field. Instead of assigning a single metric to a link, it is possible to assign different metrics depending on the TOS value of the data. Multi-protocol label switching (MPLS). Multi-protocol label switching (MPLS) tries to combine some of the properties of virtual circuits with the flexibility and robustness of datagrams. MPLS is very much associated with the Internet Protocol's datagram-based architecture. It relies on IP addresses and IP routing protocols to do this job. MPLS-enabled routers also forward packets by examining relatively short fixed-length labels, and these labels have local scope, just like an virtual circuit network. Three main things used in MPLS. To enable IP capabilities on devices that do not have the capability to forward IP datagrams in the normal manner. To forward IP packets along explicit routes, pre-calculated routes that don't necessarily match those that normal IP routing protocols would select. To support certain types of virtual private network services. MPLS Destination-Based Forwarding. Destination-Based Forwarding. The idea of attaching labels to IP packets is called threaded indices. A very similar idea is now implemented in MPLS-enabled routers. The following example shows how this idea works. Each of the two routers on the far right, R3 and R4, has one connected network with prefixes 18.1.1/24 and 18.3.3/24. The remaining routers, R1 and R2, have routing tables that indicate which outgoing interface each router would use when forwarding packets to one of those two networks. When MPLS is enabled on a router, the router allocates a label for each prefix in its routing table and advertises both the label and the prefix that it represents to its neighboring routers. This advertisement is carried in the label distribution protocol. A. R2 allocates labels and advertises bindings to R1. B. R1 stores the received labels in a table. C. R3 advertises another binding and R2 stores the received label in a table. Router R2 has allocated the label value 15 for the prefix 18.1.1 and the label value 16 for the prefix 18.3.3. After allocating the labels, R2 advertises the label bindings to its neighbors. In this case, we see R2 advertising a binding between the label 15 and the prefix 18.1.1 to R1. The meaning of such an advertisement is that R2 has said, in effect, please attach the label 15 to all packets sent to me that are destined to prefix 18.1.1. R1 stores the label in a table alongside the prefix that it represents as the remote or outgoing label for any packets that it sends to that prefix. There is another label advertisement from router R3 to R2 for the prefix 18.1.1 and R2 places the remote label that it learned from R3 in the appropriate place in its table. At this point, we can look at what happens when a packet is forwarded in this network. Suppose a packet destined to the IP address 18.1.1.5 arrives from the left to router R1. R1 in this case is referred to as Label Edge Router LER, and LER performs a complete IP lookup on arriving IP packets and then applies labels to them as a result of the lookup. In this case, R1 would see that 18.1.1.5 matches the prefix 18.1.1 in its forwarding table and that this entry contains both an outgoing interface and a remote label value. R1 therefore attaches the remote label 15 to the packet before sending it. When the packet arrives at R2, R2 looks only at the label in the packet, not the IP address. The forwarding table at R2 indicates that packets arriving with the label value of 15 should be sent out interface 1 and that it should carry the label value 24 as advertised by router R3. R2 therefore rewrites or swaps the label and forwards it on to R3. What has been accomplished by all this application and swapping of labels? Observe that when R2 forwarded the packet in this example, it never actually needed to examine the IP address. Instead, R2 looked only at the incoming label. Thus, we have replaced the normal IP destination address lookup with a label lookup. To understand why this is significant, it helps to recall that although IP addresses are always the same length, IP prefixes are of variable length, and the IP destination address lookup algorithm needs to find the longest match, the longest prefix that matches the high order bits in the IP address of the packets being forwarded. By contrast, the label forwarding mechanism just described is an exact match algorithm. It is possible to implement a very simple exact match algorithm, for example, by using the label as an index into an array, where each element in the array is one line in the forwarding table. Note that while the forwarding algorithm has been changed from longest match to exact match, the routing algorithm can be any standard IP routing algorithm, example OSPF. The path that a packet will follow in this environment is the exact same path that would have followed if MPLS were not involved, the path chosen by the IP routing algorithms. All that has changed is the forwarding algorithm. An important fundamental concept of MPLS is illustrated by this example. Every MPLS label is associated with a forwarding equivalence class FEC, a set of packets that are to receive the same forwarding treatment in a particular router. In this example, each prefix in the routing table is an FEC. That is, all packets that match the prefix 18.1.1, no matter what the low order bits of the IP addresses are, get forwarded along the same path. Thus, each router can allocate one label that maps to 18.1.1 and any packet that contains an IP address whose high order bits match that prefix can be forwarded using that label. As we will see in the subsequent examples, FECs are very powerful and flexible concept. FECs can be formed using almost any criteria. For example, all the packets corresponding to a particular customer could be considered to be in the same FEC. Returning to the example at hand, we observe that changing the forwarding algorithm from normal IP forwarding to label swapping has an important consequence. Devices that previously did not know how to forward IP packets can be used to forward IP traffic in an MPLS network. The most notable early application for this result was to ATM switches, which can support MPLS without any changes to their forwarding hardware. ATM switches support the label swapping forwarding algorithm just described, and by providing these switches with IP routing protocols and a method to distribute label bindings, they could be turned into label switching routers, LSRs, devices that run IP control protocols but use the label switching forwarding algorithm. More recently, the same idea has been applied to optical switches of the sort described. Before we consider the purported benefits of turning an ATM switch into an LSR, we should tie up some loose ends. We have said that labels are attached to packets, but where exactly are they attached? The answer depends on the type of link on which packets are carried. When IP packets are carried as complete frames, as they are on most link types including Ethernet, token ring and PPP, the label is inserted as a shim between the layer 2 header and the IP or other layer 3 header. However, if an ATM switch is to function as an MPLS LSR, then the label needs to be in a place where the switch can use it, and that means it needs to be in the ATM cell header, exactly where one would normally find the VCI and VPI fields. Having now devised a scheme by which an ATM switch can function as an LSR, what have we gained? One thing to note is that we could now build a network that used a mixture of conventional IP routers, label edge routers, and ATM switches functioning as LSRs, and they would all use the same routing protocols. To understand the benefits of using the same protocols, consider the alternative. We see a set of routers interconnected by virtual circuits over an ATM network, a configuration called an overlay network. At one point in time, networks of this type were often built because commercially available ATM switches supported higher total throughput than routers. Today, networks like this are less common because routers have caught up with and even surpassed ATM switches. However, these networks still exist because of the significant installed base of ATM switches in network backbones, which in turn is partly a result of ATM's ability to support a range of capabilities such as circuit emulation and virtual circuit services. In an overlay network, each router would potentially be connected to each of the other routers by a virtual circuit. But in this case, for clarity, we have just shown the circuits from R1 to all of its peer routers. R1 has 5 routing neighbors and needs to exchange routing protocol messages with all of them. We say that R1 has 5 routing adjacencies. By contrast, the ATM switches have been replaced with LSRs. There are no longer virtual circuits interconnecting the routers. Thus, R1 has only one adjacency with LSR1. In large networks, running MPLS on the switches leads to a significant reduction in the number of adjacencies that each router must maintain and can greatly reduce the amount of work that the routers have to do to keep each other informed of topology changes. A second benefit of running the same routing protocols on edge routers and on the LSRs is that the edge routers now have a full view of the topology of the network. This means that if some link or node fails inside the network, the edge routers will have a better chance of picking a good new path than if the ATM switches rerouted the affected VCs without the knowledge of the edge routers. Note that the step of replacing ATM switches with LSRs actually achieved by changing the protocols running on the switches, but typically no change to the forwarding hardware is needed. That is, an ATM switch can often be converted to an MPLS LSR by upgrading only its software. Furthermore, an MPLS LSR might continue to support standard ATM capabilities at the same time as it runs the MPLS control protocols in what is referred to as ships in the night mode. More recently, the idea of running IP control protocols on devices that are unable to forward IP packets natively can be extended to optical switches and TDM devices such as solid multiplexers. This is known as Generalized MPLS or GMPLS. MPLS Explicit Routing. Explicit Routing. MPLS provides a convenient way to add capabilities similar to source routing of IP networks, although the capability is more often called explicit routing rather than source routing. One reason for the distinction is that it usually isn't the real source of the packet that picks the route. More often, it is one of the routers inside a service provider's network. This figure shows an example of how the explicit routing capability of MPLS might be applied. This sort of network is often called a fish network because of its shape. The routers R1 and R2 form the tail, R7 is at the head. Suppose that the operator of the network has determined that any traffic flowing from R1 to R7 should follow the path R1, R3, R6, R7, and that any traffic going from R2 to R7 should follow the path R2, R3, R4, R7. One reason for such a choice would be to make good use of the capacity available along the two distinct paths from R3 to R7. We can think of the R1 to R7 traffic as constituting one forwarding equivalence class, and the R2 to R7 traffic constitutes a second FEC. Forwarding traffic in these two classes along different paths is difficult with normal IP routing because R3 doesn't normally look at where traffic came from in making its forwarding decisions. Because MPLS uses label swapping to forward packets, it is easy enough to achieve the desired routing if the routers are MPLS enabled. If R1 and R2 attach distinct labels to packets before sending them to R3, thus identifying them as being in different FECs, then R3 can forward packets from R1 and R2 along different paths. Instead, a new mechanism is needed. It turns out that the protocol used for this task is the Resource Reservation Protocol (RSVP). It is possible to send an RSVP message along an explicitly specified path, example R1, R3, R6, R7, and use it to set up label forwarding table entries along that path. One of the applications of explicit routing is traffic engineering, which refers to the task of ensuring that sufficient resources are available in a network to meet the demands placed on it. Controlling exactly on which paths the traffic flows is an important part of traffic engineering. Explicit routing can also help to make networks more resilient in the face of failure using a capability called fast reroute. For example, it is possible to pre-calculate a path from router A to router B that explicitly avoids a certain link L. In the event that link L fails, router A could send all traffic destined to B down the pre-calculated path. The combination of pre-calculation of the backup path and the explicit routing of packets along the path means that A doesn't need to wait for routing protocol packets to make their way across the network or for routing algorithms to be executed by various other nodes in the network. In certain circumstances, this can significantly reduce the time taken to reroute packets around a point of failure. One final point to note about explicit routing is that explicit routes need not be calculated by a network operator as in the above example. There are a range of algorithms that routers can use to calculate explicit routes automatically. The most common of these is called Constrained Shortest Path First CSPF, which is like the link state algorithms described in section 4.2.3, but which also takes constraints into account. For example, if it was required to find a path from R1 to R7 and that could carry an offered load of 100 Mbps, we could say that the constraint is that each link must have at least 100 Mbps of available capacity. CSPF addresses this sort of problem. MPLS, Virtual Private Networks and Tunnels. Virtual Private Networks and Tunnels. It turns out that MPLS can be thought of as a way to build tunnels, and this makes it suitable for building VPNs of various types. The simplest form of MPLS VPN to understand is a Layer 2 VPN. In this type of VPN, MPLS is used to tunnel Layer 2 data, such as Ethernet frames or ATM cells, across a network of MPLS-enabled routers. Reason for tunnels is to provide some sort of network service, such as multicast, that is not supported by some routers in the network. The same logic applies here. IP routers are not ATM switches, so you cannot provide an ATM virtual circuit service across a network of conventional routers. However, if you had a pair of routers interconnected by a tunnel, they could send ATM cells across the tunnel and emulate an ATM circuit. The term for this technique within the IETF is pseudo-wire emulation. We have already seen how IP tunnels are built. The router at the entrance of the tunnel wraps the data to be tunneled in an IP header, the tunnel header, which represents the address of the router at the far end of the tunnel and sends the data like any other IP packet. The receiving router receives the packet with its own address in the header, strips the tunnel header, and finds the data that was tunneled, which it then processes. An MPLS tunnel is not too different from an IP tunnel, except that the tunnel header consists of an MPLS header rather than an IP header. Looking back to our first example, we saw that router R1 attached a label 15 to every packet that is sent towards prefix 18.1.1. Such a packet would then follow the path R1, R2, R3, which each router in the path examining only the MPLS label. Thus, we observed that there was no requirement that R1 only send IP packets along this path. Any data could be wrapped up in the MPLS header and it would follow the same path because the intervening routers never look beyond the MPLS header. In this regard, an MPLS header is just like an IP tunnel header 10. The only issue with sending non-IP traffic along a tunnel, MPLS or otherwise, is this: what to do with non-IP traffic when it reaches the end of the tunnel. The general solution is to carry some sort of demultiplexing identifier in the tunnel payload that tells the router at the end of the tunnel what to do. It turns out that an MPLS label is a perfect fit for such an identifier. An example will make this clear. Let's assume we want to tunnel ATM cells from one router to another across a network of MPLS-enabled routers. Further, we assume that the goal is to emulate an ATM virtual circuit, that is, cells arrive at the entrance or head of the tunnel on a certain input port with a certain VCI and should leave the tail end of the tunnel on a certain output port and potentially different VCI. This can be accomplished by configuring the head and tail routers as follows. The head router needs to be configured with the incoming port, the incoming VCI, the demultiplexing label for this emulated circuit, and the address of the tunnel end router. The tail end router needs to be configured with the outgoing port, the outgoing VCI, and the demultiplexing label. Once the routers are provided with this information, we can see how an ATM cell would be forwarded. 1. An ATM cell arrives on the designated input port with the appropriate VCI value 101 in this example. 2. The head router attaches the demultiplexing label that identifies the emulated circuit. 3. The head router then attaches a second label, which is the tunnel label that will get this packet to the tail router. 4. Routers between the head and tail forward the packet using only the tunnel label. 5. The tail router removes the tunnel label, finds the demultiplexing label, and recognizes the emulated circuit. 6. The tail router modifies the ATM VCI to the correct value, 202 in this case, and sends it out to the correct port. One item in this example that might be surprising is that the packet has two labels attached to it. This is one of the interesting features of MPLS. Labels may be stacked on a packet to any depth. This provides some useful scaling capabilities. In this example, it enables a single tunnel to carry a potentially large number of emulated circuits. The same techniques described here can be applied to emulate many other Layer 2 services, including frame relay and Ethernet. It is worth noting that virtually identical capabilities can be provided using IP tunnels. The main advantage of MPLS here is the shorter tunnel header. Before MPLS was used to tunnel Layer 2 services, it was also being used to support Layer 3 VPNs. We won't go into the detail of Layer 3 VPNs, which are quite complex. See the further reading section for some good sources of more information, but we will note that they represent one of the most popular uses of MPLS today. Layer 3 VPNs also use stacks of MPLS labels to tunnel packets across an IP network. However, the packets that are tunneled are themselves IP packets, hence the name Layer 3 VPNs. In a Layer 3 VPN, a single service provider operates a network of MPLS-enabled routers and provides a virtually private IP network service to any number of distinct customers. That is, each customer of the provider has some number of sites, and the service provider creates the illusion for each customer that there are no other customers on the network. The customer sees an IP network interconnecting his own sites and no other sites. This means that each customer is isolated from all other customers in terms of both routing and addressing. Customer A can't send packets directly to customer B and vice versa. Customer A can even use IP addresses that have also been used by customer B. The basic idea is illustrated as in layers 2 VPNs, MPLS is used to tunnel packets from one site to another. However, the configuration of the tunnels is performed automatically by some fairly elaborated use of BGP, which is beyond the scope of this book. In summary, MPLS is rather versatile tool that has been applied to a wide range of different networking problems. It combines the label swapping forwarding mechanism that is normally associated with the virtual circuit networks with the routing and control protocols of IP datagram networks to produce a class of network that is somewhere between the two conventional extremes. This extends the capabilities of IP networks to enable, among other things, more precise control of routing and support of a range of VPN services. Protocol Independent Multicast (PIM). The Protocol Independent Multicast (PIM) routing protocols are being developed by the Interdomain Multicast Routing (IDMR) working group of the IETF. IDMR is planned to develop a set of multicast routing protocols which, independent of any particular unicast routing protocol, can provide scalable internet-wide multicast routing. Of course, PIM requires the existence of a unicast routing protocol. The major proposed and used multicast protocols perform well if group members are densely packed and bandwidth is not a problem. However, the fact that DVM-RP periodically floods the network and the fact that MOSPF sends group membership information over the links make these protocols not efficient in cases where group members are sparsely distributed among regions and the bandwidth is not plentiful. To address these issues, PIM contains two protocols. PIM dense mode, PIM-DM, which is more efficient when the group members are densely distributed, and PIM sparse mode, PIM-SM, which performs better in cases where group members are sparsely distributed. Although these two algorithms belong to PIM and they share similar control messages, they are essentially two different protocols. A. R4 sends join to RP and joins shared tree. B. R5 join shared tree. C. RP builds source-specific tree to R1 by sending join to R1. D. R4 and R5 build source-specific tree to R1 by sending joins to R1. Protocol Independent Multicast Dense Mode PIM-DM. PIM-DM is very similar to DVM-RP and uses the RPM algorithm for forming delivery trees. However, there are major differences between these two algorithms. Although PIM-DM requires the presence of a unicast routing protocol for finding routes back to the source node, PIM-DM is independent of the mechanisms employed by any specific unicast routing protocol. This is different from DVM-RP and MOSPF protocols. DVM-RP uses RIP-like exchange messages to build its unicast routing table, and MOSPF relies on OSPF link state database. The other difference between PIM-DM and DVM-RP is that PIM-DM forwards multicast messages on all downstream interfaces until it receives prune messages, while DVM-RP forwards multicast traffic to child nodes in the delivery tree. Therefore, it is obvious that PIM-DM needs to deal with duplicated messages. However, this method is chosen to eliminate routing protocol dependencies and avoid the overhead caused by the calculation of child interfaces at each router. Similar to DVM-RP, graph messages are used for attaching a previously pruned branch to the delivery tree. Protocol Independent Multicast Pairs Mode PIM-SM. PIM-SM has two key differences with existing dense mode protocols DVM-RP, MOSPF, and PIM-DM. In PIM-SM protocol, routers need to explicitly announce their will for receiving multicast messages of multicast groups, while dense mode protocols assumes that all routers need to receive multicast messages unless they explicitly send a prune message. The other key difference is the concept of core or rendezvous point RP, which have been employed in PIM-SM protocol. Each pairs mode domain has a set of routers acting as RPs, RP set. Furthermore, each group has a single RP at any given time. Every router which wants to receive multicast messages from a certain group needs to send a join message to the RP of that group. Each host has a designated router, DR, which is the router connected to the same subnetwork with the highest IP address. When a DR receives an IGMP message indicating the membership of a host to a certain group, the DR finds the RP of that group by performing a deterministic hash function over the sparse mode region's RP set and forwards a unicast PIM join message to the RP. The DR and intermediate routers create an entry in their multicast forwarding table for the star group pair, star means any source, such that they can know how to forward multicast messages coming from the RP of the multicast group to the DR and group members. When a source sends a message to a certain group, the DR of that source encapsulates the first message in a PIM-SM register packet and sends it to the RP of that group as a unicast message. After receiving this message, the RP sends back a PIM join message to the DR of that source. While this message is being forwarded to the DR, all intermediate routers add a new entry in their multicast forwarding table for the new source group pair. This way, next multicast messages of this source can be forwarded to the RP easily. Obviously, RP will be responsible for forwarding these multicast messages to the members of the group. It should be noted that until these entries have been added in all intermediate routers tables, all multicast messages will be forwarded as encapsulated unicast messages. Although forwarding multicast messages through a shared RP tree is sufficient, if the number of participants or messages being transmitted through the shared tree increases, using the same shared tree may not be very desirable. PIM-SM provides a method for using shortest path trees for some or all of the receivers. PIM-SM routers can continue using the RP tree but have the option of using source-based shortest path trees on behalf of their attached receivers. In these situations, the PIM-SM router sends a join message to the source node. After the source-based shortest path delivery tree is constructed, the router can send a prune message to the RP, removing the router from the RP tree. Reverse path broadcast. Reverse Path Broadcasting (RPB). An even more efficient solution than building a single spanning tree for the entire internet would be to build a group-specific spanning tree for each potential source subnetwork. These spanning trees would result in source-routed delivery trees emanating from the subnetwork directly connected to the source station. Since there are many potential sources for a group, a different spanning tree is constructed for each active source group pair. RPB tree from source A. RPB tree from source C. Operation. The fundamental algorithm to construct the source-routed trees is referred to as reverse path broadcasting (RPB). For each source group pair, if a packet arrives on a link that the local router considers to be the shortest path back to the source of the packet, then the router forwards the packet on all interfaces except the incoming interface. Otherwise, the packet is discarded. The interface over which the router expects to receive multicast packets from a particular source is referred to as parent link. The outbound links over which the router forwards the multicast packet are called the child links. The basic algorithm can be enhanced to reduce unnecessary packet duplication if the router making the forwarding decision can determine whether a neighboring router on a potential child link considers the local router to be on its shortest path back to the source, that is, on the remote router's parent link for the source group pair. If this is the case, then the packet is forwarded to the neighbor. Otherwise, the datagram is not forwarded on the potential child link because the neighboring router will be required to discard the packet since it arrives on a non-parent link for the source group pair. The information needed to make this downstream decision is relatively easy to derive from a link state routing protocol since each router maintains a topological database for the entire routing domain. If a distance vector routing protocol is employed, a neighbor can either advertise its previous hop for the source group pair as a part of its routing update message or Poisson reverse the route. Either of these techniques allows an upstream router to determine if a downstream neighboring router considers it to be on the downstream router's shortest path back to the source. Benefits and limitations. The key benefit to reverse path broadcasting is that it is reasonably efficient and easy to implement. It does not require that the router know about the entire spanning tree, nor does it require a special mechanism to stop the forwarding process as flooding does. In addition, it guarantees efficient delivery since multicast packets always follow the shortest path from the source station to the destination group. Finally, the packets are distributed over multiple links, resulting in better network utilization since a different tree is computed for each source group pair. One of the major limitations of the RPB algorithm is that it does not take into account multicast group membership when building the distribution tree for a source group pair. As a result, datagrams may be unnecessarily forwarded to subnetworks that have no members in the destination group. Reverse Path Multicast (RPM). Reverse Path Multicasting (RPM) is an enhancement to the reverse path broadcasting and truncated reverse path broadcasting. RPM creates a delivery tree that spans only subnetworks with group members and routers and subnetworks along the shortest path to subnetworks with group members. RPM allows the source-routed spanning tree to be pruned so that datagrams are only forwarded along branches that lead to members of the destination group. Operation. When a multicast router receives a packet from a source group pair, the first packet is forwarded following the TRPB algorithm to all routers in the internetwork. Routers that are at the edge of the network and have no further downstream routers in the TRPB tree are called leaf routers. The TRPB algorithm guarantees that each leaf router receives the first multicast packet. If there is a group member on one of its leaf subnetworks, a leaf router forwards the packet based on its IGMP information. If none of the subnetworks connected to the leaf router have group members, the leaf router may transmit a prune message on its parent link informing the upstream router that it should not forward packets for the particular source group pair on the child interface receiving the prune message. Prune messages are sent only on hop back towards the source. An upstream router receiving a prune message is required to record the prune information in memory. If the upstream router has no local recipient and receives prune messages on each of the child interfaces that it used to forward the first packet, the upstream router does not need to receive additional packets for the source group pair. This means that the upstream router can generate a prune message of its own one hop back toward the source. This succession of prune messages creates a multicast forwarding tree that contains only live branches, that is, branches that lead to active group members. Since both the group membership and the network topology are dynamically changing, the pruned state of the multicast forwarding tree must be refreshed at regular intervals. Periodically, the prune information is removed from the memory of all routers and the next packet for the source group pair is forwarded to all leaf routers. This results in a new burst of prune messages, allowing the multicast forwarding tree to adapt to the ever-changing multicast delivery requirements of the internetwork. Limitations. Despite the improvements offered by the RPM algorithm, there are still several scaling issues that need to be addressed when attempting to develop an internet-wide delivery service. The first limitation is that multicast packets must be periodically forwarded to every router in the internetwork. The second drawback is that each router is required to maintain state information for all groups and each source. The significance of these shortcomings is amplified as the number of sources and groups in the multicast internetwork expands. The multicast backbone MBONE. A logical network imposed over the top of the internet in which multicast enhanced routers use tunneling to forward multicast datagrams across the internet. The multicast backbone MBONE is an interconnected set of subnetworks and routers that support the delivery of IP multicast traffic. The goal of the MBONE is to construct a semi-permanent IP multicast test bed to enable the deployment of multicast applications without waiting for the ubiquitous deployment of multicast-capable routers in the internet. The MBONE is a virtual network that is layered on top of sections of the physical internet. It is composed of islands of multicast routing capability connected to other islands by virtual point-to-point links called tunnels. The tunnels allow multicast traffic to pass through the non-multicast capable parts of the internet. IP multicast packets are encapsulated as IP over IP, so they look like normal unicast packets to intervening routers. The encapsulation is added on entry to a tunnel and stripped off on exit from a tunnel. This set of multicast routers, their directly connected subnetworks, and the interconnecting tunnels define the MBONE. Since the MBONE and the internet have different topologies, multicast routers execute a separate routing protocol to decide how to forward multicast packets. The majority of the MBONE routers currently use the Distance Vector Multicast Routing Protocol (DVMRP), although Some portions of the M-bone execute either multicast OSPF, MOSPF, or the Protocol Independent Multicast PIM routing protocols. The M-bone carries audio and video multicast of IETF meetings, NASA Space Shuttle missions, US House and Senate sessions, and live satellite weather photos. The Session Directory (ST) tool provides users with a listing of the active multicast sessions on the M-bone and allows them to define or join a conference. Conclusion. In this chapter, we have covered the following in detail: the multicast backbone, M-bone, link state multicast, distance vector multicast, reverse path broadcast, reverse path multicast RPM, protocol independent multicast PIM, multi-protocol label switching MPLS, destination-based forwarding, explicit routing, virtual private networks VPNs, and tunnels.